NENOMATICA, where mathematics meets YouTube excellence. Welcome to this video on the domains of algebraic expressions. Today, we'll explore the set of values for which an algebraic expression is defined. The domain of an algebraic expression is the set of values that the variable can take for which the expression is well defined. In other words, it's the range of input values for which we can calculate a real output. Let's start with a formal definition. The domain of an algebraic expression is the set of all values that the variable can take without making the expression undefined. Now, let's examine the first case, polynomial expressions. A polynomial is an expression that consists of variables and coefficients, involving only the operations of addition, subtraction, multiplication, and non-negative integer exponents. Examples of polynomials include expressions like x squared minus 3x minus 1, or 1/3 x cubed minus 2x squared plus x minus 1. The domain of any polynomial is the set of all real numbers, because a polynomial is defined for every real value of x. Let's visualize what this means. Here's the graph of our first example polynomial x squared minus 3x minus 1. Notice that this is a continuous function that extends infinitely in both directions. We can substitute any real value for x, and we'll always get a valid output. For polynomial expressions, the rule is simple. The domain is always the set of all real numbers. Now, let's move to the second case, rational expressions. A rational expression is a fraction where both the numerator and denominator are polynomials. For example, the expression x squared minus 4 divided by x minus 2. This is a rational expression because both the numerator and denominator are polynomials. For rational expressions, the domain consists of all real numbers except the values that make the denominator equal to 0. This is because division by 0 is undefined in mathematics. Now, let's visualize our example rational expression. The numerator is x squared minus 4, and the denominator is x minus 2. To find the domain, we need to find where the denominator equals 0. Let's solve x minus 2 equals 0. This gives us x equals 2. So, the domain of this rational expression is all real numbers except x equals 2. On the graph, we can see a vertical asymptote at x equals 2, which represents the point where the function is undefined. For rational expressions, the rule is find the values that make the denominator 0 and exclude those from the domain. Let's solve an example together. Find the domain of the rational expression, x squared plus 1, divided by x squared minus 9. First, we recognize this is a rational expression with the numerator p, x, equals x squared plus 1, and the denominator q, x, equals x squared minus 9. To find the domain, we need to find where the denominator equals 0. Let's solve x squared minus 9 equals 0x squared minus 9 equals x plus 3 times x minus 3 equals 0. This gives us x equals negative 3 or x equals positive 3. Therefore, the domain of this rational expression is all real numbers except x equals negative 3 and x equals positive 3. We can write this in set notation as x belongs to the real numbers such that x is not equal to negative 3 and x is not equal to 3. Let's summarize what we've learned about the domain of algebraic expressions. For polynomial expressions, the domain is always all real numbers. This is because polynomials are defined for every value of x. For rational expressions, the domain is all real numbers except the values that make the denominator equal to 0. This is because division by 0 is undefined. When determining the domain of an algebraic expression, first identify whether it's a polynomial or a rational expression, and then apply the appropriate rule. Welcome to our lesson on finding the domain of rational expressions. Understanding the domain is crucial when working with rational expressions, as it identifies where these expressions are defined. The domain of an expression is the set of all input values for which the expression is defined. For rational expressions, the main restriction is that we cannot divide by 0. So we need to identify values that would make the denominator equal to 0 and exclude them from the domain. Let's start with our first example. Find the domain of the expression 8x plus 5 divided by 2. To find the domain, we need to determine when the denominator equals 0. In this case, the denominator is simply the constant 2, which never equals 0. Since the denominator never equals 0, there are no restrictions on the domain. Therefore, the domain is all real numbers. Let's move on to our second example. Find the domain of the expression 7 plus x divided by x. Again, we need to determine when the denominator equals 0. In this case, the denominator is x, which equals 0 when x equals 0. Since the denominator equals 0 when x equals 0, we must exclude this value from the domain. Therefore, the domain is all real numbers except 0. For our final example, find the domain of the expression 2b plus 1 divided by 2b minus 1. As before, we need to determine when the denominator equals 0. Let's set the denominator equal to 0 and solve for b. We've found that when b equals 1/2, the denominator equals 0. Therefore, we must exclude b equals 1/2 from the domain. Let's summarize what we've learned about finding domains of rational expressions. For the expression 8x plus 5 divided by 2, the domain is all real numbers since the denominator is a constant that's never 0. For the expression 7 plus x divided by x, the domain is all real numbers except 0 because the denominator equals 0 when x equals 0. For the expression 2b plus 1 divided by 2b minus 1, the domain is all real numbers except b equals 1/2 because that's where the denominator equals 0. Remember, to find the domain of a rational expression, identify the values that make the denominator 0 and exclude them from the set of all real numbers. A rational function is a fraction where both the numerator and denominator are polynomials. The key concept to remember is that the domain of a rational function includes all real numbers except those that make the denominator equal to 0. Let's look at our first example. We have the rational function 2x minus 3 divided by x squared minus 4. First, we need to find the values that make the denominator equal to 0. We can factor the denominator as x squared minus 4 equals x minus 2 times x plus 2. So, setting each factor equal to 0, x minus 2 equals 0 gives us x equals 2. And x plus 2 equals 0 gives us x equals negative 2. Therefore, the domain of our rational function is all real numbers except x equals 2 and x equals negative 2. In set notation, we write this as the set of real numbers minus the set containing negative 2 and 2. Let's visualize this domain on a number line. Our domain includes all real numbers except at x equals negative 2 and x equals 2, which are shown as holes in the number line. Now, let's look at our second example. We have the rational function 3x divided by x squared plus 4. Again, we need to find the values that make the denominator equal to 0. The denominator is x squared plus 4. Can this expression ever equal 0? Actually, for any real value of x squared will always be greater than or equal to 0. Adding 4 to that gives us a value that is always greater than 0. So, there are no real values of x that make this denominator 0. Therefore, the domain of this rational function is all real numbers. In set notation, we write this as simply the set of real numbers. Let's visualize this domain on a number line. In this case, the domain includes all real numbers with no exclusions. Let's examine our third example. We have the rational function a plus 5 divided by a squared minus 5 a plus 6. As always, we start by finding values that make the denominator equal to 0. Let's factor the denominator. A squared minus 5 a plus 6 equals a minus 2 times a minus 3. Setting each factor equal to 0. A minus 2 equals 0 gives us a equals 2. And a minus 3 equals 0 gives us a equals 3. Therefore, the domain of this rational function is all real numbers except a equals 2 and a equals 3. In set notation, we write this as the set of real numbers minus the set containing 2 and 3. Let's visualize this domain on a number line as well. Our domain includes all real numbers except at a equals 2 and a equals 3. Let's summarize what we've learned about finding the domain of rational functions. First, identify the denominator of the rational function. Second, determine the values that make the denominator equal to 0 by solving the equation denominator equals 0. Finally, express the domain as all real numbers except those values that make the denominator 0. Remember to use proper set notation when expressing your answer. We need to find the domain of the rational expression 2y divided by y times quantity 2y minus 6. To find the domain, we need to identify the values of y that make the denominator equal to 0. The denominator is y times 2y minus 6. Let's factor the denominator further. We can take out the common factor of 2, which gives us y times 2 times y minus 3. Now we need to find values that make this denominator equal to 0. The denominator equals 0 when either y equals 0 or y minus 3 equals 0, which means when y equals 3. Since we can't have y equal to 0 or y equal to 3 in the denominator, we exclude these values from the domain. The domain is the set of all real numbers except 0 and 3, which we write as the set of real numbers minus the set containing 0 and 3. Let's move on to our second example. We need to find the domain of the rational expression 5x divided by 3ab squared. In this example, we have multiple variables. The denominator is 3ab squared. We need to identify when this expression equals 0. The denominator 3ab squared equals 0 when either a equals 0 or b equals 0. Note that 3 is a constant and never equals 0. Since we have multiple variables, we express the domain as the set of ordered pairs, a, b, and are squared such that it is not equal to 0 and b is not equal to 0. Let's summarize what we've learned. To find the domain of a rational expression, we need to identify all values that make the denominator equal to 0 and exclude them from the domain. For an expression with one variable, we write the domain as the set of all real numbers excluding the values that make the denominator 0. For expressions with multiple variables, we express the domain as a set of ordered pairs or tuples, excluding the combinations that make the denominator 0. Remember this key rule. For a rational expression p of x divided by q of x, the domain is the set of all real numbers x such that q of x is not equal to 0. This rule is the foundation for finding domains of all rational expressions. Welcome to our lesson on odd root expressions and their domains. Today, we'll explore why expressions with odd roots like the cube root are defined for all real numbers. Let's start by understanding what odd roots are. An odd root is any root where the index is an odd number, such as the cube root, which has an index of 3, the fifth root with an index of 5, and so on. The key property of odd roots that we need to understand is this. For any real number, its odd root always exists, and is also a real number. This is different from even roots, which can give us complex numbers when applied to negative values. Let's see some examples. When we take the cube root of 8, which is positive, we get 2. That's easy to understand. But what about when we take the cube root of a negative number, like -8? We get -2, which is still a real number. We can visualize this on a number line. For any point on the number line, whether positive or negative, we can always find its cube root, which will also be a point on the number line. For positive numbers, the cube root is positive. For negative numbers, the cube root is negative. And for 0, the cube root is 0. Now, let's focus on case 3 from our example, which deals with expressions that include an odd root of a linear term. A linear term is an expression like 2x minus 5, where x appears with a power of 1. Let's clarify with a rule. For any odd root function, such as the cube root, the domain is the set of all real numbers. This is because odd roots can handle both positive and negative inputs, as well as 0. So when we have the cube root of 2x minus 5, we can apply our rule. Since the cube root is an odd root, this expression is defined for all real values of x. It doesn't matter what value 2x minus 5 takes, whether it's positive, negative, or 0, we can always find its cube root in the real number system. Let's evaluate this expression with different values of x to demonstrate that it's defined everywhere. If x equals 3, then 2x minus 5 equals 1, and the cube root of 1 is 1. If x equals 2, then 2x minus 5 equals -1, and the cube root of -1 is -1. If x equals 2.5, then 2x minus 5 equals 0, and the cube root of 0 is 0. Welcome to our lesson on domain recognition for even roots. Today we'll learn the crucial concept that the expression under an even root must be non-negative for the root to be defined. In an expression with an even root, like a square root, the domain consists of all values that make the expression under the radical non-negative. This is because even roots of negative numbers are not defined in the real number system. Let's look at our first example. We have the square root of x plus 5. Since a square root is an even root, the expression under the radical must be non-negative. For this expression to be defined in the real number system, we need the expression under the radical to be non-negative. So we need x plus 5 to be greater than or equal to 0. Now, let's solve this inequality for x. Subtracting 5 from both sides, we get x is greater than or equal to negative 5. Therefore, the domain of the square root of x plus 5 is all values of x that are greater than or equal to negative 5. We can write this in interval notation as the closed interval from negative 5 to infinity. Now, let's look at a more complex example. We have the square root of x plus 5 plus the square root of the quantity 1 over x plus 2 plus the square root of the quantity x plus 5. For this expression to be defined, we need both square roots to have non-negative expressions under them. Let's look at each part separately. Let's solve the first inequality. For negative 1 over x plus 2 to be non-negative, it must be greater than or equal to 0. Since the numerator is negative 1, the denominator must be negative for the fraction to be non-negative. So we need x plus 2 to be less than 0. Now, let's solve the second inequality. For 1 over x plus 5 to be non-negative, since the numerator is positive, the denominator must also be positive. So x plus 5 must be greater than 0. To find the domain of the entire expression, we need to find values of x that satisfy both conditions simultaneously. We need x to be less than negative 2 and greater than negative 5. This gives us x between negative 5 and negative 2. So our final answer is: the domain of this expression is the set of all x such that negative 5 is less than x and x is less than negative 2. In interval notation, this is the open interval from negative 5 to negative 2. Remember, when working with even roots, the expression under the radical must always be non-negative. This is a fundamental rule that helps us determine the domain of such expressions. When dealing with multiple even roots, find the domain for each part and take their intersection to get the final domain. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.